Hello everyone. So today we're going to talk about some useful tricks that we can use for daily lives, well, especially for students in elementary school or middle school when they try to learn something about integers or multiplications or divisions. Now, why would I say that? Well, here is what we're going to do. First, I believe most of you have already know how to check whether a number is a multiple of 2 or 5, which is pretty easy. We just look at our last digits of the number. Of course, we're talking about an integer, or you can just think of the natural numbers in the moment. But it's the same thing. But when we say that, we mean we just need to look at the last digits. If it is an even number or ends with 0, 2, 4, 6, or 8, we know that that number is an even number. In other words, it must be divisible by 2 or a multiple of 2. Similarly, if that number ends with a 5 or 0, we know that that number is divisible by 5, or in other words, it's a multiple of 5. Now, perhaps most of you have already known there is also a trick to check whether an integer is a multiple of 3 or even is a multiple of 9 or not. But of course, some of you might not know. So here is a trick. Let's say if we have a number listed this way. Well, generally saying we'll list it like this. And let me give you an example. Such as the number 321. Well, this is clearly a multiple of 3, right? But let's say if we don't know, how can we quickly check if it is a multiple of 3? Well, that trick tells us we just need to add all the digits together and see what we end up with. If the result is a multiple of 3, then the original number is also a multiple of 3. Otherwise, it is not. Fair enough. So let's check. We have 3 plus 2 plus 1, which is equal to 6. And we know that 6 is a multiple of 3. So that tells us the number 321 is also a multiple of 3. Let's check another example. Now, this time I'm trying to make something that's bigger. Let's say 487,561. So I just randomly make a number. Let's see what we'll get. And I shouldn't put an equal sign. Remember, they are not equal. But following from the trick, we will now add all the digits together. We get 4 plus 8 plus 7 plus 5 plus 6 plus 1. Okay, let's see. So 4 plus 8 is 12, 7 plus 5 is also 12, 12 plus 12 is giving us 24, plus 6 is 30, plus 1 is 31. So 31 is clearly not a multiple of 3. And we can apply this one more time to with that trick and try to do it one more time, giving us 3 plus 1, which is equal to 4. Well, now we have a single digit. We know that this is clearly not divisible by 3. So what does that mean? It means that this number here, 487,561, is not a multiple of 3. Good. The similar trick will also work for multiple of 9. So let's get a few more examples. Such as 784. Let's see. Well, if we add all the digits together, we get 7 plus 8 plus 4, which gives us 15 plus 4, which is 19. So it means that it's not a multiple of 9, because 19 is not a multiple of 9 either. Well, let's do one more example for multiple of 9 and see if it's right. So such as, let's pick 9 to the 4th power, which is 6,561. So if we use the same trick, we're going to add all the digits together, 6 plus 5 plus 6 plus 1, which gives us 6 plus 5 is 11, plus 6 gives us 17, plus 1 is 18. And of course, 18 is a multiple of 9. And if we use that trick, we can just confirm that this number, 6,561, is also a multiple of 9. Now, we of course check that it is true because this is 9 to the 4th power. So this is how the trick works. But why is it true? I guess most of you might not know. So today we're going to explain why these tricks work. And to explain how it works, we will think it with, again, is because we're playing with numbers. We're going to use the ideas in number theory. So we're going to do the following. Consider any integer. Let's keep it positive. So we're going to deal with natural numbers in the form like this. This means that we have n plus 1 digits. So we start with a to the n minus 1, all the way down to a1, a0, with this bar on top. Here it means that in itself, regularly we will think that it's a multiplication. This is just a whole integer that is expressed this way, where a0 is actually the single digits place. This is a 10. This is a 10 digit, so on and so forth. So in this expression, we can just break it down into the following. So let's get an example. If we think of the number 123, what it really means in this symbol is representing, we have 3 in the 0th place. Well, I shouldn't call it 0. The 1 place, meaning that we have 3 copies of 1. Plus, we now have 2 here, which means we have 2 copies of 10 to the 1st power. And then we also need to add 1 here, which means 1 copy of 100, which is 10 to the 2nd power, so on and so forth. So let's say if we add a few more digits, let's say if we have a 6 here, and then a 0 here, and then a 7 here, then we are going to continue it. So we will get plus 6 times 10 to the 3rd power, because we have 6 copies here, plus 0. This is a placeholder. We don't have to write it, but if we write it, we'll make sure that we won't miss any place or any position. So we have 0 copy in the 10 to the 4th power, or 10,000. And then we're gonna add 7 copies of 10 to the 5th power, etc., etc. So this is what it really means in this symbol. Now if we generalize it, we're going to get the following. So we start with the most right, which is the digits right next to the decimal point, which we don't write it when we know that it's an integer. So this tells us that we have a to the 0, no, not a to the 0, a0 copies of 1, or in our words, it will be 10 to the 0th power. And then next we have a1 copies of 10 to the 1st power, and then so on and so forth, which ends up with the following: an to minus 1 copies of 10 to n minus 1st power, plus an, or copies of 10 to the nth power. Great. So we have a finite sum here. Then next, we're going to see how we can change it into something that we are trying to get, which is something that has the same look as the trick. Now, keep in mind, since we're only trying to check whether a number is a multiple of 3 or 9 only, meaning that after we divide by 9, we don't care what the quotient is, we only care about what the remainder is. So it doesn't really matter how big that number is, we don't have to worry about it. And since we're trying to find the remainder, again, we can use modulus. So we're going to use modular arithmetic to help us get the answer quickly and see why we can actually get the trick. Following from it, let's start with divide by 9. We're going to do modulus 9. Because once we do modulus 9, we'll quickly see why it works for 3 as well. So let's see. Since we're doing modulus 9, it means that if we see any number that is not between 0 to 8, remember, not including 9, we would like to change it such that that number becomes a number that's between 0 to 8. Especially, in particular, we wanted to get into an integer that's between 0 to 8. Okay, so what does that mean? Well, we have 10 here, the base 10 here. So 10 is bigger than 9. Since we only want to find the remainder, we're going to divide by 9 and see what the remainder of 10 is after dividing by 9. So if we do that, 10 divided by 9 is equal to 1. And then we are going to subtract it, we get remainder 1. In other words, in modulus 9, 10 is congruent to 1, so we can now replace all the 10s by 1. Meaning, instead of having a plus a0 times 10 to the 0th power plus a1 times 10 to the 1st power, and then so on and so forth up to an times n to 10 to the nth power, we now can rewrite the expression into a0 times 1 to the 0th power plus a1 times 1 to the 1st power plus etc. until we hit a to n minus 1, a n minus 1 times 1 to the n minus 1st power plus an times 1 to the nth power. Good. So now let's try to simplify. Well, now we have 1 to the 0th power, 1 to the any power. We have 1 as the base. So since we have 1 in the base, we know that 1 to any power is just equal to 1. Okay? Meaning that if we just simplify it, we just end up with a0 times 1, which is just a0, plus a1 times 1, again, it's just a1, plus etc. until we hit the last two terms, an minus 1 plus an. And keep in mind, we're doing it in mod 9. Meaning that we're we're dividing by 9 and see what the remainder is. Good. Now, we just get the expression that we want, but how is it going to help? Well, here's the last thing. In order to know whether the original number is a multiple of 9 or not, we say we can just check whether the remainder part is multiple of 9 or not. Okay, why? Because if here is going to give us 0, meaning that there is no remainder, then by the congruent classes, it means that the original number also has no remainder after divided by 9. Okay, remember, congruence means that they have the same remainder. So these two expressions will have the same remainder, so that if the last part here has a remainder equal to 0, it will be the same as the initial part, which is the original positive integer, is also having the remainder equal to 0. In other words, it will be divisible by 9. Now, similarly, if this sum right here does not congruent to 0 after mod 9, meaning if they don't, if the remainder is not equal to 0, then with the similar argument, we can claim that the original number, the positive integer we start off, is also not a multiple of 9 because the remainder will also not be 0. Good. So we just see why it works for dividing by 9 now. So we can do the similar argument for 3. The only thing we need to change is now, instead of dividing by 9 or do modulus 9, we're going to do modulus 3 and see if there's anything we need to change, or we just need to check if everything is still the same. So the first step is still the same because this is how we define the expression of a positive integer or any integer. Then if we are going to divide by 3, we now need to check what the base become. So 10 divided by 3 is going to give us 3, but 3 times 3 is 9. So after the subtraction, we still have the remainder 1. Meaning, now we're going to change the base from 10 to 1 again. So everything is still the same, and we will end up with the same results. Therefore, the trick of adding all the digits will work for checking the divisibility of 3 and 9. And this is not just a coincidence. It can be proved in this way. So the last thing that I'm going to mention and give it to you guys as a homework assignment is try to find a trick of checking the divisibility of 7. Okay? And of course, just knowing the trick is good, but it will be even better if you can understand or explain why the trick works. Just like how we explain why the trick of adding the digits work for checking divisibility of 3 and 9. That's it. Thank you for watching. I will see you guys next time.